Okay, let me just make one change of notation. Now you see, when we are talking about rotations, basically we can talk about active or passive rotations. So for example, active rotation if this is your vector v, after a rotation your vector just becomes this one. This is your rotation angle theta. Now passive rotation this is your vector v. After a rotation, your vector v stays the same. Your axis change. You see, active rotation by theta is in terms of its effects in the components of vectors, it's the same thing as a passive rotation by minus theta. So there is this sign difference. Now what we have been discussing here is starting from 0 is kind of the passive rotation. This is the coordinate axis that are always changing. But the convention is usually the active rotation. You are actually changing your state. Now the main difference in our results will be just mx will go to minus mx, my will go to minus my, mz will go to minus mz. That's the only difference. And well, instead of changing theta, you can just change the definition of the generators. So the rotation matrix is still 1 minus I theta m. Either you change theta or you change the sign of m to go from active rotations to passive rotations. So you just change the m's. So you get the commutation relations mx my is equal to I mz, not minus I mz. And hence jx jy is plus I jz. Again, not minus jz. It's basically a change of notation. Change of convention. Now, any questions? So what we were saying is, if you want to describe rotations in our Hilbert space, just find 3 operators, jx, jy, that satisfy this commutation relation. Now let's look at spin 1/2. We already have such operators. You see, if you remember, we had Sx, which was h power over 2, plus minus, plus minus plus, Sz, which was h power over 2, plus plus, minus minus minus, and Sy, well, let me check the signs. No, Sz is minus. So this I h power over 2 plus minus with a minus sign plus minus plus. Well, again, let me just make sure that I have the correct signs everywhere. Yes. Let's calculate their commutation relations. Not using matrices, but just using operators. Now, Sx, Sy. This is equal to h bar over 2 times minus I h bar over 2 plus minus plus minus plus times sy is minus plus minus plus minus plus. This is equal to minus I h bar over 2 squared. Let's see, with plus minus, I have to multiply this one to get a non-zero contribution. That would give me plus plus. And with this minus plus operator, I have to multiply with this one, so that gives me minus, minus, minus. Well, you can just look at the other way around, sy, sx. This will be I h bar over 2 squared. Well, sy, sx is nothing but sx, sy dagger. Since s operators are Hermitian themselves, that this dagger operation just changes their order. So this is equal to I h bar over 2 squared plus plus minus minus minus. So if I look at the commutator, sx, sy minus sy, sx, this is twice h bar over 2 times h bar over 2 plus plus minus minus minus. But this is nothing but sz. So the commutator of sx, sy is equal to, I also have an I times h bar times sz. Now you can look for the other commutators and you will see that sy, sz is equal to I h bar sx, sz, sx is equal to I h bar sy. So these are the commutation relations that my rotation operators should satisfy. So I already have my three operators that satisfy the commutation relations of generators of rotation. Now let's see, what about the expectation values? What happens to the expectation values if I consider some rotations? Now, before continuing, okay, so I have this, let's say, ket alpha, let's look at Sx alpha, and let's look at rotations around the z-axis. If I rotate my system around the z-axis, this will become the rotated alpha, Sx times the rotated alpha. But this rotated alpha is just e to the power minus I over h bar jz, or in this case it will be sz, let's say rotation by an angle theta. So this expectation value of Sx after the rotation becomes the expectation value of e to the power I over h bar sz theta Sx e to the power minus I over h bar sz theta. Well, let's calculate that operator. I have e to the power I over h bar sz theta Sx e to the power minus I over h bar sz theta. Well, we know the Baker-Hausdorff formula. This will be equal to Sx plus I over h bar theta sz Sx. Well, let's do it in two different ways. Let's look at this operator first. E to the power minus I over h bar sz of theta. What is this operator? Now we know what sz is. This is h power over 2 plus plus minus minus minus. If I look at sz squared, it just becomes h bar squared over 4 plus 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 minus minus. Or this is h bar squared over 4 times the identity operator. So sz to some even power, sz squared, sz to the 2m power is nothing but h bar over 2 to the power 2n times 1. sz to an odd power, this will be h bar over 2 to the power 2n times sz. So let's look at the e to the power minus I over h bar sz of theta. This is sum over n, 1 over n factorial, minus I over h bar theta to the power n, sz to the power n. Well, I can just separate it into odd powers and even powers. N from 0 to infinity, 1 over 2n factorial, minus I over h bar theta to the power 2n, sz to the power 2n. These are the even powers, plus n from 0 to infinity, 1 over 2n plus 1 factorial, minus I over h bar theta to the 2n plus 1, sz to the power 2n plus 1. These are the odd powers, which is equal to n from 0 to infinity, 1 over 2n factorial, minus 1 to the power n, theta over h bar times h bar over 2 to the power n. Because sz to the power n is just h bar over 2 to the power 2n times the identity operator, plus or minus I n from 0 to infinity, 1 over 2n plus 1 factorial, sz, let me see, minus 1 to the power n, that is minus I to the power 2n plus 1. I took one of the minus i's out. Well, let me also take over h bar also out. Minus I over h bar. What remains inside will be theta to the power 2n plus 1. sz to the power n is h bar over 2 to the power 2n times sz. This is equal to well, let me see. Here I have theta over h bar to the power 2n plus 1. Now this h bar is not out. I just took one minus I out. Okay, so here what we have, n from 0 to infinity, minus 1 to the power n divided by 2n factorial, theta over 2 to the power 2n times 1, minus I sz, n from 0 to infinity, minus 1 to the n divided by 2n plus 1 factorial, theta over h bar, theta over 2 to the power 2n plus 1. I have one more h bar over here, And I think I have a factor of 2 over here. Did I make a mistake somewhere? Okay. And this is the first term is nothing but cosine theta over 2 times the identity operator minus I 2 over h bar sz times, no, the first sine theta over 2. Now here I use the fact that sz is an operator corresponding to spin 1/2. So it's squared is identity operator. Now let's go back. What we were trying to calculate this one over here. The rotated expectation value of Sx. This is equal to cosine theta over 2 well, let me just write it out. I have cosine theta over 2 times 1 minus 2I over h bar sz sine theta over 2 times Sx. Now this is plus times cosine theta over 2 plus 2I over h bar sz sine theta over 2. Now let's multiply them. I have cosine squared theta over 2 times Sx. It's the product of the first terms. Then I have 2I over h bar cosine theta over 2 sine theta over 2 times Sx Sz plus, no, this is minus, okay, Sx Sz comes with a minus sign plus Sz Sx comes with a plus sign. There I have a commutator. And then I have plus 4 over h bar squared Sz squared sine squared theta over 2. Now Sz Sx Sz sine squared theta over 2. So I have these four terms. Now Sz Sx commutator was just h bar sy, I h bar sy. Now let's look at this one, Sz Sx Sz. Can I simplify it? Well, let me give it a try. This is Sz, Sx Sz minus Sz Sx plus Sz Sx. This is Sz. Well, this product, this commutator is minus I h bar sy plus Sz squared Sx this is equal to minus I h bar Sz sy. Well, Sz squared is h bar squared over 4 Sx. Now let's calculate this one, SZ, SY. Well, this is SZ and SY, so if we multiply them, I get h bar over 2, h bar squared over 4 times I. Well, with this one, I have to multiply this one to get a non-zero contribution. And that gives me plus minus. And with this one, I have to multiply with the second terms together to get a non-zero contribution. That gives me minus plus. But this is nothing but I times h power over 2 Sx. So let's go back. We were looking at Sz, Sx, Sz. We first showed that this is equal to minus I h bar Sz, Sy plus h bar squared over 4 Sx. Now Sz, Sy is I h bar over 2 Sx plus h bar squared over 4 Sx. This is equal to h bar squared over 2 plus h bar squared over 4 Sx. No, sorry, I think I made a mistake here somewhere. Plus, if I multiply this, the first terms, I get a minus sign over here. Plus minus. The second terms, I get a minus sign. And again, minus plus. So this is minus I h bar over 2 Sx. So here, this is plus, so this is minus. So Sz, Sx, Sz, it just turns out to be minus h bar squared over 4 Sx. Now, we were looking at this thing. This was equal to, well, the expectation value of this product. Well, that product we were simplifying. And so that product just became this one. Now this one over here is I h bar Sy. And we had shown that this product is minus h bar squared over 4 Sx. So this is equal to Sx. After rotation, it just becomes expectation value of Sx cosine squared theta over 2 minus sine squared theta over 2 plus expectation value of Sy times 2I over, no, let me write it in a slightly different form, I over h bar, no, 2I over h bar, I h bar, cosine theta over 2, sine theta over 2. So the rotated Sx for a rotation around the z-axis, the expectation value is nothing but the expectation value of Sx multiplied by cosine theta. h bars cancel, minus the expectation value of sy times sine theta. So what does this tell me? You see, this is nothing but the rotation expression of how the x component of a vector changes under a rotation around the z-axis. So basically, everything we are doing turns out to be consistent with each other. As x operator is a vector, the x component of a vector, and under rotations, it just rotates properly, just like the x component of a vector should be. Now, of course, here there's a, let's say, a slight catch, let's say. Here we made several use of the fact that we are dealing with spin 2 operators. Spin 1/2 particles, sorry. So we don't really know whether this will work if we have an arbitrary spin. But we can also prove that. Let's see. Let's go back to our first expression. In fact, let's look at how the jx expectation value of the jx component changes. Under rotations around the z-axis. So it can be spin 1/2, but they can be any spin. Now let's look at this one. This is I over h bar jz theta, jx e to power minus I over h bar jz theta. Well, we can use the Baker-Hausdorff formula to calculate this. This is nothing but jx plus I theta over h bar, commutator of jz with jx, plus 1 over 2 factorial I theta over h bar squared, jz, commutator with jz, jx, etc. Now let's look at what these commutators are. Now jz, jx, we already know what it is. This is equal to I h bar jy. This is the definition of these operators. Let's take one more commutator. This is I h bar, commutator of jz with jy, because jz, jx commutator is I h bar jy, and this is equal to I h bar times minus I h bar jx. Well, we started with jx. In 2 steps, we are back in jx. So let's add one more. This is equal to minus 1 times I h bar squared jz, jx, because this commutator over here is minus 1 I h bar squared jx, and jz, jx is I h bar jy. So here we have 3 commutators, and we end up having I h bar cube. And you see, if you look at the commutators, we have the first term is jx, the second term is jy, the third term is jx, the fourth term is jy, the fifth term will be jx, and so we just continue like this, jx, jy, jx, jy in all these terms. In all these terms appearing in our expansion. E to the power I over h bar theta jz, jx e to the power minus I over h bar theta jz. This will be equal to jx. Well, the next term is just the commutator of jz and jx, I h bar jy, this plus I over h bar theta times I h bar jy. plus 1 over 2 factorial I over h bar theta squared. This is that square is this factor over there. And then we have the commutators, and that commutator is minus 1 I h bar squared jx. So we are back in jx. Now the next term, 1 over 3 factorial I over h bar theta cube. Then we have minus 1 times I h bar cube jy, etc. And again, this will be just jx times cosine theta minus jy times sine theta, if you just sum up the terms. So if you start with jx and rotate your state, what you obtain is jx cosine theta minus jy sine theta. So your state is rotated. Again, here I didn't use the fact that we are dealing with spin 1/2. The only thing I used is that these j operators satisfy this commutation relation. ji jj is equal to I epsilon I jk jk. And these j's, we said that they are generating rotation, so we had identified how they change might get, and we said that they should satisfy these commutation relations. As long as they satisfy these commutation relations, well, they just give me how just the components of a vector should change under rotations. I don't need to take any explicit form for these j's. As long as they satisfy this commutation relation, they will describe rotations. They will generate rotations. Now, there's kind of a funny thing. You see, if you rotate by 2 pi, the expectation value of jx just becomes the expectation value of initial expectation value of jx. Nothing really changes in the expectation values. But if you look at how the states themselves are modified, this is the operator that modifies my kets. E to the power minus I over h bar sz 2 pi this is equal to minus 1. So after a rotation by 360 degrees, my kets do not go back to their initial kets. Well, there's no problem with the expectation values because the expectation values contains Abra and the ket, both of which change their sign. But the kets do not change, do not go back to their initial value after a rotation by 2 pi. If it's a spin 1/2, of course. You should rotate your system by 720 degrees to recover your initial ket. May I take your coffee? You see, there's a classical analog to this one also. It's a property of the rotations. You see, just take this one and rotate it by 360 degrees. Okay, you see the hole is on this side. Okay, how do you do that? Okay, so it rotated by 360 degrees. The cup is almost in its initial state, but not my arm. I should keep rotating it. Okay, so if I make a rotation, of course, if I want to rotate it more, I cannot really turn my arm longer, but I can do this thing. I just rotate it in the same direction. And now it's back to, the cup is back in its original configuration, and so is my arm. So somehow these spin 1/2 particles, they can feel this property, that a 360 rotation is not the same thing as 720-degree rotation. It is due to this 1/2 over there. This factors of 1/2, it causes the fact that a rotation by 2 pi causes my state to acquire a minus sign. And that factor 1/2 can be measured. And we have a verification of this. Now, we will discuss it on Wednesday. Any last minute questions? So see you on Wednesday.